Okay, so welcome back to another video. So in today's video, we're actually going to talk in depth about Bernoulli numbers. And Bernoulli numbers are these sequence of rational numbers such that it's defined as the following. So what we have here on the top is in terms of a generating function, and these other two, they're equivalently equal to each other, are defined in terms of a recurrence relation. So we have generating functions. You see x divided by e to the power x minus 1 is equal to this infinite sum of b sub n times x to the power n, then divided by n factorial. And then the recurrence relation is 1 for n is equal to 0, and the negative infinite sum for n choose k of b sub k divided by n plus 1 minus k for n is strictly greater than 0. Similarly, in this situation, you can write the same. As I said, it's the same thing as negative 1 divided by n plus 1 times the infinite sum of n plus 1 choose k b sub n for n is greater than 0. So the outline of how we're actually going to go through discussing Bernoulli numbers is, as of course I already give out the definitions and it's a rational sequence. I'm going to just take a little bit of a tangent. We'll talk about a little bit of history and what some applications it's used / where does it appear. And then we're actually going to cover some different proofs. Two of them, well rather three. Two proofs is that this actually has a nice relationship using Bernoulli's numbers. And then another proof is actually a lemma that we'll be proving that will help support one of the proofs that we will be proving. So with that, let's actually get into a little discussion what Bernoulli numbers is all about. So the Bernoulli numbers, they were actually first discovered by Swiss mathematician Jacob Bernoulli when they were named, and eventually it was independently named by Japanese mathematician Seki Takakazu. The whole idea was published in 1712, and the appearances where it makes is that, for one, it actually makes its appearance for Taylor series expansions of the tangent and the hyperbola tangent functions. Faulhaber's formula for the sum of nth powers of the first n positive integers, the Euler-Maclaurin formula, which is basically a formula for the difference between an integral and a closely related sum, and of course it's appeared in certain values of the Riemann Zeta function, which we will prove in today's video. That is going to be one of our proofs. That's actually it's the Riemann Zeta functions at the even integers where it utilizes the Bernoulli numbers. So the sequence, for example, if you write the list out explicitly, is that we have b sub 0 is equal to 1, just like this definition over here. We have b sub 1 is equal to negative 1/2, b sub 2 is equal to 1 over 6, b sub 4 equals negative 1 over 30, b sub 6 equals 1 over 42, the list goes on, so on and so forth. So notice that I didn't even list any of the odd indices number. So the interesting thing is that the odd indices of the Bernoulli numbers, they're actually going to equal 0. And anything with the even indices for n is greater than 0 is actually that b sub n is negative when it's divisible by 4. Otherwise, it's positive in the other situations. However, in this case, for the odd indices, that's the second proof that we're going to prove. I know I said second, but really that's actually the first proof we will, head towards that direction, because specifically that the b sub n for the odd integers actually utilizes that for when we prove for the Riemann Zeta integers, or the Riemann Zeta function at the even integers. So now that everything is said and done, then I hope you get a little crash course on what, an introduction to Bernoulli numbers. Let's actually start off with going through our first proof, which is showing that the odd indices of the Bernoulli numbers equals 0. Okay, so the first proof we're going to go over is the odd indices for the Bernoulli numbers equals 0. So what it says is that if we let b sub n be the nth Bernoulli number, then b sub 2n plus 1 is equal to 0 for n greater than or equal to 1. So the proof follows is that, so we start off with the generating function definition. So x divided by e to the power x minus 1, set this equal to the infinite sum for n is equals 0 of b sub n, and then times x to the power n divided by n factorial. Okay, so let's actually utilize the left-hand side and fix some things up. So x divided by e to the power x subtract 1, what I can do is I can write that as x divided by 2, and then multiply with 2 divided by e to the x minus 1. So we're just rewriting things like a multiply and divide by 1 situation. Okay, so let's fix this up and show that for the numerator, I can actually add a 0 term. So x divided by 2, what I'll do is I'll add and subtract an e to the power x. And then now that's going to be plus 2 divided by e to the power x subtract 1. And then fix this up even further that we're going to utilize the plus 2 fix that up to change so that this is going to be the same thing as plus and then the -1 after distributing that negative. So that sounds confusing to you. So in other words, that's the same thing as x divided by 2 multiplied with e to the power x plus 1, then quantity subtract e to the power x minus 1 and divided by e to the x minus 1. Then you'll notice that we'll have some terms that will cancel, specifically the e to the x minus 1 that'll just reduce to a 1. So that means I have x divided by 2 and then multiply with e to the x plus 1 divided by e to the x minus 1 and then, didn't mean to close that off, then subtract 1. Then I'll just distribute the x over 2 to everything. So then this is just negative x divided by 2. And then add this with x divided by 2 multiplied by e to the x plus 1 and then divided by e to the x subtract 1. So how do we actually take this step further from here? So here's what we're going to do. We're going to suppose that f of x be this function over here. So let f of x equals e to the x plus 1 divided by, or rather x divided by 2 multiplied by that quantity, x divided by 2 multiplied by e to the x plus 1 and then divided by e to the power x subtract 1. What we're going to do is we're actually going to show that f of x that we just defined is actually going to be an even function. So what I'll do is now we'll just plug in f of negative x. So f of negative x is going to be, so just replace everything for x for negative x. So negative x divided by 2, and then I have e to the negative x, add this with 1, and then divided by e to the negative x subtract 1. And so next thing I'll do is I'll multiply e to the x to both the numerator and denominator. So then that means over here I have negative x divided by 2, and then e to the, well, this is going to be a 1 since I multiplied that. So I have 1 plus e to the x and then divided by 1 minus e to the x. Okay, and so from here, what I'll do is now let's factor out the negative so that the e to the x is at the leading coefficient, and this is addition, so I'll just move that out front without any troubles. So negative x divided by 2, then e to the x plus 1, and then on the bottom is negative, and then e to the x, and then subtract 1. Okay, then close that off. And then of course the negatives will cancel for both the numerator and denominator, so that's nice. So now we're gonna have that this is gonna be just positive x divided by 2, and then multiply with e to the x plus 1, and then divided by e to the x subtract 1, which of course we just showed that this is the same function as f of x, so therefore that means that f of negative x is equal to f of x, aka an even function. So that's so far half of the proof that we're working on, so I'll get rid of everything here and then we can continue forward. Okay, and so far we have that negative x divided by 2 and then plus x divided by 2 of, e to the x plus 1 and then divided by e to the x minus 1. We earlier said that f of x, which was everything in this brace, is an even function we just showed. So next step, and you might be thinking that what was the point of all this? So going back to the beginning, we have that the generating function x divided by e to the x minus 1 is equal to the infinite sum. So n equals 0 and then b sub n times x to the power n divided by n factorial. Okay, so what we'll do is let's actually evaluate this at the term for n is equal 0 and n is equal to 1. And I mentioned earlier that b sub 1 is equal to negative 1/2 from the recurrence relation we just put in, and then b sub 0 is equal to 1. So that would mean that putting this all together, substituting, and then put it at the n equals 0 and n equals 1. So we'll have the expansion of 1 subtract 1/2 x, add this with the infinite sum where n is equal to 2 of b sub n, then x to the power n divided by n factorial. Okay, then continuing forward, I'll just add a 1/2 x to both sides. So x divided by e to the x minus 1 plus 1/2 x. Then that's set to equal 1 plus the infinite sum of just this thing right there. And so now what I'll do here is continuing forward that I'm actually just going to cross multiply and just get everything in terms of a common denominator. So doing all this, so this will be 2x and then plus x times e to the x minus 1 and then divided by 2 times e to the x minus 1. And then set this equal to this side. So I'll just denote the arrow as that's the same thing as the right-hand side. And so from here, if you reduce everything down, so equals is just denoting this side of the equation over here. If you reduce this all down, and we'll have that this is x divided by 2, and then e to the x plus 1 divided by e to the x minus 1, which of course we said that this was equal to f of x, and then this is equal to the right-hand side. So to reiterate everything that we just showed and simplify, we have everything underlined in this pink. So how do we continue something like this from before? Well, we just showed that f of x is an even function. So what I'll do is now I'll plug in negative x back into this infinite sum over here. So I have one side that's just for x, and then the opposite side being negative x when you plug it into this equation over here. So what I can do from here, the next step is that because of the even function, I'll plug in negative x for, the series expansion over here, and another side for being the x plug in. So if I plug in, for now, I'll just leave that as a positive x. So this will mean 1 plus the infinite sum n is equal to of b sub n, then x to the power n divided by n factorial is equal to, now just plug in for the negative. So that means the infinite sum n is equal to of b sub n, and then negative x to the power n, then divided by n factorial. Okay, so of course you're obviously going to see that the ones will cancel for the both sides. So now what I'm going to do here is, now we just set n to be the odds, some odd integer for n is greater than 1. So in this case, n equals, let's say 2k plus 1 for k is some positive integer. So performing all this out together, so now we're going to have something in this fashion. So I have b sub 2k plus 1, and then divided by 2k plus 1 factorial multiplied with x to the power 2k plus 1. And then on the right hand side now, I'll have b sub 2k plus 1, then divided by 2k plus 1 factorial, and then multiply with negative x to the power 2k plus 1. Okay, and so what I'll do here is just to get rid of the factorials, let's just multiply a 2k plus 1 factorial divided by x to the power 2k. And so that'll just lead us with b 2k plus 1, then multiplied by x, which is equal to b 2k plus 1 multiplied by negative x. And then what I can do here is let's just divide the x to both sides. So we're just left with b sub 2k plus 1 is equal to negative b 2k plus 1. And then add the b sub 2k plus 1 to both sides. So now that will yield us with 2 times b sub 2k plus 1 equals 0. Divide the 2 to both sides. And so therefore we lead to the conclusion that b sub 2k plus 1 is indeed equal to 0. And of course, thus for all natural numbers n, with n being greater than or equal to 1, we have that b sub 2n plus 1 is equal to 0 for the following. So this concludes our proof for the odd indices of the Bernoulli numbers vanishing just like that. So with that in mind, now let's actually move on to the next proof. Okay, so moving on to the next proof is that we have that the Riemann zeta function at the even integers, and that says that for the Riemann zeta 2n is equal to negative 1 to the power n plus 1 multiplied with b sub 2n times 2 to the power 2n minus 1 times pi to the power 2n divided by 2n factorial, b sub n being the nth Bernoulli number and n is a positive integer. But to actually start off this proof, we actually want to prove the lemma to help support this proof. So the lemma says that if we let x be a real number such that the absolute value of x is less than 1, then we have that pi times x times cotangent of pi x is equal to 1 minus 2 times the infinite sum of the Riemann zeta 2n then times x to the power 2n. So we have 3 proofs as I mentioned, so we'll actually go to the lemma first. Once proved that, then we can actually show for the Riemann zeta function the even integers is the following explicit formula. So to start off this proof, we'll actually be using Euler's infinite sign product and then using the input argument for x times pi. So that means I'll have sine of pi times x and then divided by pi times x is going to equal to the infinite sum. So from infinity and then k is equal to 1 of 1 subtract x squared divided by k squared. So with this in mind, let's actually take the natural log of both sides. So we have the natural log of sine of pi x divided by pi x, then equal to the natural log of the infinite product. So k is equal to 1 of 1 subtract x squared divided by k squared. Taking things one step ahead, we have the natural log property. So that means I have a natural log and then minus a natural log. So minus ln of pi x, I'll just add that to the opposite side. And then using continuity, we have a natural log of products. That's the same thing written as the infinite sum of the natural logs of what's inside the argument. So putting this all together, so I have the natural log of sine of pi x is going to equal to the natural log of pi x. And then add this with the infinite sum, then k is equal to 1 of the natural log of 1 minus x squared divided by k squared. And so with this in mind, so what we'll do is let's actually take the derivative of both sides. So the derivative ln of sine of pi x is 1 divided by sine of pi x. Then take the derivative of the inside. Sine of pi x, derivative of that is actually pi times cosine of pi x. So this means pi then times cosine of pi x, and then divided by sine of pi x. So let me actually put this over here. We'll write this d over dx for take the derivative. So taking the derivative of this one, this is actually just going to be 1 over pi x, then times the derivative inside, which is just pi. Pi's will cancel, so it's just 1 over x. And then add this with, now the derivative is the infinite sum. K is equal to 1 of 1 divided by 1 subtract x squared divided by k squared. And then take the derivative of the inside, which is just multiplied with negative 2x divided by k squared. Taking another step further, we use trig properties that cosine and divided by sine is the same thing as cotangent. And I'll multiply the x to both sides, so that actually gets rid of the x on the denominator. So that means we have pi times x times cotangent of pi x. This is then just equal to 1, and then add this with the infinite sum of k is equal to 1 of 1 divided by 1 subtract x squared divided by k squared. And then inside this is going to be negative 2x squared divided by k squared. You'll notice that the inside over here, we have that the absolute value of x is strictly less than 1. This is actually can be written in a geometric series going backwards. So what we'll have is that this is actually a double sum. So pi times x times cotangent of pi x is equal to 1. And then add this with the infinite sum, then k is equal to 1. And then over here, this is the infinite sum, then n is equal to 0 of x squared divided by k squared, and then to the power n multiplied with negative 2x squared divided by k squared. And then as you see over here, we can actually move the negative 2x back to the front, and then the x squared, k squared goes inside with the n. So that means putting a step further, and then I have to change our indices, of course. So that means I have 1 minus 2 times the infinite sum. So k is equal to 1, and then now change the index so that we have n is equal to 1 of x squared divided by k squared, and then to the power n. Then taking a step another further is I'm going to interchange the sum. So this is actually valid by Tonelli's theorem. And so what we have now is 1 minus 2 times the infinite sum. So that means n is equal to 1. And then to write things even further, that if I change that sum back, and rewrite things, of course. So I have the infinite sum over here, then k is equal to 1 of 1 divided by k to the power 2n, and then factor out the 2x2n outside. And so what that will yield us is that this is actually exactly the given as above. So 1, then subtract the infinite sum, or 1 subtract 2 times the infinite sum. N is equal to 1 of the Riemann zeta of 2n, and then multiply with x to the power 2n. So therefore, that actually completes the proof of our lemma just as that. So with this in mind, so we'll actually now move on to finally proving that the Riemann zeta function of the even integers has this explicit formula. Now that the lemma has been proven, so now we'll finally prove for the Riemann zeta function is this explicit formula. So utilizing the lemma, we have that starting with that left-hand side, pi x cotangent of pi x is equal to, so we don't have to do anything to the right side just yet. We're actually just going to manipulate the left-hand side of this first. So in other words, using a nice identity with exponential functions, so this is the same thing as written as I times pi times x, multiply with e to the power I times pi times x, add this with e to the negative of the same thing, and then divided by e to the I pi x, and then subtract e to the negative I pi x. So to simplify some things further, let's actually multiply a e to the power I pi x to both the numerator and denominator. And so this will yield us the following. So that means we have e to the power 2I pi x, and then add this with 1, then divided by e 2I pi x, and then subtract 1. And so to utilize the simplification further, so what I'll do is rewrite that I pi x and then fix this inside. So I have now this is e2 I pi x minus 1, then plus 2, and then divided by that denominator. Which if we now simplify all this out, then I have I pi x and then multiply with 1 plus 2 divided by e I pi, or 2. And then if we simplify all this out, so now I have I pi x and then multiply with 1, then add this with 2 divided by e to the power 2 I pi x, and then subtract 1. And so now just distribute that out. So this is just I pi x, and then add this with 2 I pi x divided by e 2 I pi x minus 1, which if you'll notice that for specifically this term over here is actually written as the same form for the generating function of the Bernoulli number, so we can substitute that in for the infinite sum over here. So we'll have I pi x, and then add this with the infinite sum at n is equals 0 of b sub n, and then times 2 I pi x, and then to the power n divided by n factorial. Okay, so with that definition in mind, so let's actually now expand the term for n is equal to 0 and n is equal to 1. As mentioned, b sub 0 is 1, and then b sub 1 is negative 1/2. So that means, and then putting everything for that term in, so we'll now have I pi x, and then add this with 1, and then subtract 2I pi x, then divided by 2, which is just reduced to just I pi x, and that'll get rid of that itself. And then continue the expansion forward for starting at n is equal to. And then once you'll notice that, of course, these two are gonna, cancel out each other, the I pi x and over here. So we're left with 1 plus the infinite sum at n is equal to of b sub n times 2 I pi x, then to the power n divided by n factorial. We can actually fix this up a bit. So in other words, I'll actually do a little clever trick. I'm actually going to factor out the negative 1/2, and multiply the 2. So in other words, I have 1 subtract 2 times the infinite sum at n is equal to of negative 1/2, and then multiply by the b sub n, then 2I pi x to the power n, and then divided by n factorial. So what was the purpose of doing that? This is actually where the next step comes in. So you'll notice is that what I'm going to do is we're actually going to expand this out, and then just from the first proof earlier that we derived that the odd Bernoulli numbers vanish equal to 0, because if you expand this out, we're going to have some odd indices and those equal 0. What we can do here is we can actually rewrite the sum such that we're actually dealing with the even indices. So performing that step ahead, what we'll do is now rewrite that as the following. So this is going to be the same thing as 1 subtract 2 multiplied by the infinite sum, then n is equal to 1 of negative 1/2, and then multiply by b sub 2n multiplied by 2I pi x to the power 2n, and then divided by 2n factorial. And so from that lemma we just proved, so we can actually set this equal to the right hand side, so 1 subtract 2 times the infinite sum at n is equal to 1 of the Riemann zeta of 2n, and then multiply with x to the power 2n. So the next thing we're going to do here is, it looks a little confusing, that we're actually going to do a clever trick and equate the coefficients of the left hand side and the right hand side, such that this term is going to equal to this term. And the interesting thing is that we can actually show that if we set Riemann zeta 2n by its own, we get this explicit formula, which indeed it does, since we'll have the following, that the Riemann zeta of 2n and then x to the power 2n is equal to just negative b 2n, and then multiply with 2 pi ix, then 2n, and then divided by 2n factorial, and then we'll multiply the 2 over here. And then actually, if you reduce all this down, then if you divide the x2n to both sides, and of course we have the negative over here, but we're dealing with the odd indices, so that actually just gets that out of the way. And we can fix this up such that we'll have it in the term of negative 1 to the n plus 1, and of course divide the 2, then subtract by the exponents. And then if you reduce all that down, we have the Riemann zeta of 2n is indeed equal to negative 1 to the power n plus 1 multiplied by b to the power, or b sub 2n, then multiplied by 2 to the power 2n minus 1, multiplied with pi divided by 2n, all this being divided by 2n factorial, which indeed completes our explicit formula that we have just shown. So this actually proves the Riemann zeta at the even integers of the explicit formula, just like that, which I think this is a very nice utilization for the Bernoulli's numbers as shown. So I hope you like what you see over here, so you can share it to everybody that has taken a liking and interest of Bernoulli's numbers and everything we just shown. So there you have it. So yeah, that's pretty cool if you ask me.